Hello, welcome to my channel. In this video, we are going to be taking a look at the Gauss law and its application. So what we want to look at is the Gauss law as one of the fundamental laws in physics. And it is very important in the study of electric fields. It gives the relationship between charges and electric field. Okay? So we have the Gauss law, which states that the net flux through any closed surface is given by this expression, where we have our flux, electric flux is equal to the electric field dot the change in area equal to the charges that are enclosed by that Gaussian surface all over the relative permittivity. So we can give more details where our Q in represents the net charge inside the surface. E represents the electric field at any point on the surface. Okay, so let's take a typical example of how we can apply this particular formula in solving a real life problem. So we have a problem of this form. An insulating solid sphere of radius A has a uniform volume charge density ρ and carries a total positive charge Q. Calculate the magnitude of the electric field at points outside and inside the sphere. So before we solve this problem, it's important for us to take note of this word insulating solid sphere. So let's see the difference the difference between if it were to be a conducting sphere. Okay, so we have first an insulating sphere. Insulating sphere, right? Most times when you charge an insulating sphere, the charges are evenly distributed throughout the entire body. But when it comes to a conducting sphere, when you charge it either positively or negatively, all the charges, because electrons can easily move, they are all gathered at the surface. So we have a conducting sphere. So that's the major difference between a conducting sphere and an insulating sphere. So we are interested in calculating the electric field inside this region and outside this region. So we'll start with this solution. So we have, recall this formula, right, which we would usually start with. So we just need this part, right? Because we know our Q, we are interested in calculating the electric field. We no longer need this part. So at this point, so let's consider the sphere that we are considering. So this is sphere, an insulating sphere. We are interested in calculating the electric field at this part. So it could be anywhere around. So the R here is starting from the center to any point here. This point here is a Gaussian surface, right? So we're interested in calculating the effect of this at this point. So the electric field at this point as a result of this charge Q, right? Okay, so what we need to do is to reproduce our E integral of dA equal to Q all over E naught. You can see our Q here is this particular one here, all over relative permittivity. Then our E is independent of this dA. So it's not a function of A here. So that's why it's a constant, it comes out. So if we integrate over the entire surface of this sphere, because it's an arbitrary surface, which is also known as a Gaussian surface. If we integrate this expression, it gives us A. And what is the area of A sphere? It gives us 4 pi r squared. So, and we have E times 4 pi r squared equal to Q all over E naught. So we can make E the survey formula. And we have E equal to Q all over 4 pi E naught r squared. Now recall that 1 all over 4 pi E naught is same thing as K. So we have E equal to KQ all over R squared, right? So this is our R. As long as it is greater than A, then this particular formula holds. Now, if you notice, this formula is very popular and it's unique to a point charge. The electric field at any point away from a point charge. So it's also equivalent to even if it's a solid object, right? So let's take a look at the next problem for electric field inside the sphere. So we take a look at this diagram. So this is a solid sphere. This is a solid sphere and it is totally charged. Remember, in our previous slide, we had that as long as it's an insulating sphere, all the charges are gathered or evenly distributed around this particular charge. So the electric field at any point R, which is less than A, any point here, can be determined. And this is how you can determine it. We recall our formula, phi equal to this and expression. Now we no longer need this part, it's just this part that we need. And from here we get this expression Remember, our Q is supposed to be Q all over E naught. But this entire solid is Q. But what we want is just this part. So we can no longer use Q for this part again. We can no longer use Q. So we'll replace this Q with a formula which is related to what? The charge density. So we use the charge density, which is equal to Q all over V. If this V is the volume of this entire surface, then this charge density is for this entire surface. But if this V is just for this inner circle, inner Gaussian surface, then this charge will be for just this particular solid of this radius R. So we have our Q equal to rho V. So we replace Q with rho V, and we have E dA equal to rho V. But now this our V must not be the volume of this entire one, but it must be the volume of this inner one. And what's the volume of this inner one? It will be 4 over 3 pi r cube. So we have this expression. So we have rho all over E naught 4 pi r cube all over 3. So at this point, we can pause here and come to this part. So what is the area of that inner Gaussian surface? It will be what? 4 pi r squared. So at this point, we can eliminate these parts, and we have our E equal to rho r all over 3 E naught. Our R here must be less than A. We would have stopped here, but if this density is not given, if this charge density is not, we can replace this charge density in terms of that our Q. So we recall that our Q is equal to rho times the volume. Q is equal to rho times the volume. If the volume there, this R that is supposed to be here, it takes the A, then this particular charge density times this volume must be equal to the total charge if R becomes A. But if R becomes just normal R, it's no longer equal to this one. So at this point, wherever we see rho, we can replace with what? Q times this particular expression. So it's like making rho the Soviet formula, right? Because the initial question we're given Q. We know the value of Q. So we want to replace our rho with Q, and we have this expression. So at this point, we have electric field is equal to rho all over 3. That's R all over 3 E naught. Then our rho here will be replaced by this expression, which is this. So if we cancel out, right, we have this Q times R, because 3 will take care of 3 all over this. And remember, 1 all over 4 pi E naught is K. So finally, our E is equal to K QR all over this. So our answer can be in this form or in this form, as long as R is less than A over R is less than A. So this E here is in terms of the Q, and this E here is in terms of the charge density. So whatever is given, you can use any one of them. Now, for electric field inside and outside a spherical conducting sphere. So imagine for a conducting sphere, the electric field inside a spherical conducting sphere is 0. Always 0. Why? Because if we consider a conducting sphere, all the charges are gathered at the surface. So if we take a Gaussian surface inside there, no charge will be enclosed. So the electric field inside here will be 0, compared to that of an insulating charge. While at the surface, while outside, the electric field outside a spherical conducting sphere is usually what? E is equal to KQ over R squared, which tallies with that of an insulating sphere. So that's it. So I hope this helps. Please like, share, and follow for more. Thank you.